Today's seminar. I'm happy to have Dr. Daniel Gershman with us today. Dan received his PhD in space and planetary physics from the University of Michigan and currently works as part of the Geospace Physics Laboratory at NASA Goddard Space Flight Center. His research spans a multitude of space environments, including planetary magnetospheres, magnetosheaths, and interplanetary space. He's conducted research as part of the MESSENGER, MMS, and Juno mission science teams, and has studied magnetic reconnection, solar wind magnetosphere coupling, wave particle interactions, and magnetic turbulence. Today, I'm happy to have Dan here with us to talk about external energy inputs into planetary magnetospheres.
All right, so afternoon, everyone. Thanks for joining. Sorry, we have some technical difficulties, so we'll manage. Grateful my audio is actually working. Really what I'm talk about is kind of the energy reservoirs that are available at planetary magnetospheres. Focus a little bit on in particular, the external ones like the solar wind and the sun, and then kind of talk about how that impacts different systems in the solar system. So if you don't mind going to the next slide 2.
Yep.
Okay, so one of the things that motivates this is thinking about the energy crises that appear at the different planets. And so this is a plot of different thermospheric temperatures of the outer planets, the ice giants and the gas giants, Jupiter, Saturn, Uranus, and Neptune. If you take how much heating you can expect just from the sun, so the solar EUV input that would heat the thermosphere, you get thermospheric temperatures that are much, much, much lower than what we actually observe, both with in situ spacecraft and remote sensing observations or things that are around each planet. And so you have this energy crisis, which is what's actually heating the thermosphere if it's not the sun. And so you have to think about the different reservoirs of available energy. And so this isn't necessarily, some of those are going to be internal to the planetary system, and some of them are going to be external, an interaction not just from the solar EUV, but also the solar wind itself. So if you go to the next slide, which, we think about, we worry a lot about magnetospheres, and of course that the solar wind is not just the light that's actually providing some energy, it's also the solar wind upstream of these obstacles. You do have the rotation of the planet and plasma that's internal to some of these systems, in particular Jupiter and Saturn, that provide a lot of internal energy. But you do get this interaction between the solar wind and the planetary magnetic field and plasmas there that does allow for energy input and exchange to the system. Next slide, please. So one of the things that seems to be pretty ubiquitous is that it's clear that you can get energy from a planetary magnetosphere. This is evidenced by just the fact that you see aurora at the different planets. So you get these beautiful, large-scale, persistent aurora at Jupiter and Saturn, and you can even see some weaker emissions at Uranus and another wavelengths with Neptune. And so we know that when you see things like that and you have a magnetosphere coupled system, you have energy input in the form of auroral precipitation, so the particles themselves. You'll have Poynting flux, so electromagnetic field energy, and Joule heating associated with sort of the convection of those magnetic field lines above the poles that sort of generates this focused input of energy into these systems at high magnetic latitudes, even if they're not actually high latitudes geographically. And then you have this question of like, okay, well, I have all this energy that's coming in. How do I redistribute it around the planet? And that's really, they're pieces to these energy crises that need to be resolved. Not only where can I get the energy, but also how can I actually get it to where it needs to be so that I can lead to sort of a global thermospheric temperature increase. So if you go to the next slide, please. And so this is still an unsolved problem in a lot of ways on Earth. It's less so because a lot of our thermospheric heating is from the sun, but we still don't quite know how all of that is heated. And we know we have a lot of contribution of thermospheric heating from geomagnetic storms, geomagnetic activity, and so the coupling between the magnetosphere, ionosphere, thermosphere is still really an open question. And so I do want to give a plug for the GDC mission out of NASA, the Geospace Dynamics constellation, that's really intended to go after this at Earth, and the things that we can learn from that in terms of how the high latitude responds to magnetospheric forcing, and all the internal processes in this case at Earth that globally redistribute the mass, momentum, and energy. And these will supplement, in a lot of ways, some other processes that happen specifically to some of the giant planets. But the same kind of physics we're going after here, and this coupling between these systems, is really important, not just at Earth, of course, but also for thinking about how this happens at other planets. Next slide, please. And in the case of Jupiter and Saturn, while we know that the magnetosphere provides a lot of energy input through auroral precipitation, it's pretty clear at those planets that those are really internally driven processes. And so you have a lot of really strong internal plasma sources at Jupiter and Saturn. They generate magnetodisks, and there's lots of centrifugal and rotational effects that lead to sort of a systematic, really strong J cross B forces and auroral acceleration at these planets. And so those are, the source of energy from the magnetosphere is ultimately pretty internal, although there are some dynamics that might be explained by external phenomena. On the contrast, when you go further out at Uranus and Neptune, which don't nominally have really strong internal sources in their magnetospheres, but do have auroral emissions, they've been given less study, and also it's not clear exactly what's providing that energy, and even thinking about how much energy you need is not something that's been given a lot of attention. That's something that we wanted to think about. Go to the next slide, please. So there's a few ways that you can get energy transfer from the solar wind to the magnetosphere, and that's really what we want to think about at these different planets. And so in the top, you can see you have reconnection, which we'll spend some time talking about, where you do have this, in particular at the day side, reconnection coupling the magnetic fields that'll lead to magnetic field convection. It'll lead to particle heating and transport of mass and energy into the magnetosphere. And the bottom two I'm going to kind of lump together. It's really this diffusive boundary transport, or Kelvin-Helmholtz, that happen along the flanks, and you do get mixing and exchange of mass and energy into magnetosphere from the solar wind. And you can imagine that the type of energy input that's dominant depends both on what the magnetosphere looks like, the magnetosphere configuration, and also what the upstream solar wind is doing. And certain conditions will be more conducive than others, and different planets might behave in different ways. Next slide, please. And so there's certainly a variety of planetary magnetospheric configurations. The ones that we deal with in our solar system are largely the ones on the right, where you have this supersonic solar wind and this bullet-shaped magnetosphere. Within some of the planetary magnetospheres, like in Jupiter, and with the case of Ganymede, or even when you get extreme conditions at Earth. Recently, MMS recorded low Alfvénic Mach number upstream at Earth, and you can get things like Alfvén wings sorting. In particular, that also can happen at Mercury. And there may be some exotic environments, in particular, in exoplanets, where you're in the configuration on the left really all the time, depending on if you have a planet that's really close to its host star. And so it's important to think about the variations and the different types of coupling that you can get for these different geometries. Go to the next slide, please. One thing that we did was look at the variation of solar wind, sort of big parameters as you go out throughout the heliosphere, and what was observed by the full range, both inner and outer heliosphere, with Helios and Voyager and Pioneer spacecraft. One thing you see is that and then this occurred over decades, and so over several solar cycles. So one thing you see in the top panel is that the solar wind dynamic pressure, when you scale for R squared, so scale for heliocentric distance, is pretty rock solid. It's pretty constant. There's some variation there, but really pretty constant and scales as r squared. And whether you're at solar min or solar max, it's a pretty predictable thing. One thing that does vary quite a bit is the magnetic pressure in the solar wind, which is the second panel. What you can kind of see is that it has different variations, is one inside the inner heliosphere, inside the orbit of Earth, and then sort of settles out as you get past the orbit of Earth. And then you see this variation. One thing that's really clear when you look out at the end of this plot, you look at Voyager 2, which went out further, its radial heliocentric distance is coupled with the solar cycle. And so you can actually see it exhibits sort of the magnetic pressure. Second panel exhibits this sinusoidal oscillation as you go from solar min to solar max. That's the entire magnetic field of the heliosphere going systematically up when you have increased solar activity and systematically down when you're in solar minimum. And so when you combine these things together to get an important parameter like alpha Inuk Mach number in the solar wind, see it's really low in the inner heliosphere, below 10, and then kind of saturates out in the outer heliosphere. All four of the planets kind of see the same thing with the modulation provided by the solar activity. Go to the next slide, please.
Dan, we had 2 blank slides,
Oh.
which I think we missed. The next slide is mass and energy transport at the magnetopause.
What's on it?
This has the solar wind and Earth and magnetic reconnection.
Okay, got it. Sorry about that.
No problem.
Yeah, so really what we're talking about here now is focus a little bit on magnetic reconnection, which is the process through which you're going to combine the solar wind interplanetary magnetic field and that of the Earth. Go to the next slide, please. So the one thing that we did was actually look at this, and lots of people have over the decades kind of thought about this at different planetary environments. And one thing that becomes clear is that reconnection, it requires certain conditions to onset. But you can apply those conditions to a lot of environments. And so when you think of, and then to say the top panel on the left, which is typical fast reconnection and a stable X line, you have magnetospheric and magnetosheath plasmas coming together and forming an outflow, and reconnection happens, and you have this conversion of magnetic energy to particle energy. Some things then, and then there's a bunch of things that can stop that from happening. So the next panel down is diamagnetic drift, suppressed reconnection, and so when that X line, essentially because the gradient across the density gradient across that magnetopause boundary is so strong, the X line actually drifts faster than the outflow can outflow, and that stops reconnection from happening. Other things that can happen is you can have really strong velocity shear, and then so the third panel there, you can see that it really looks a lot more like Kelvin-Helmholtz or instability or vortices forming, which can still require mixing, but is not necessarily reconnection, or the fast reconnection that you see in the top panel. And then you can also have 3D effects where out of plane small scales can suppress the actual current sheet and out of plane current from forming. But one thing in particular with the case of diagmatic suppression, which is pretty easy to study in different environments, if you look at Earth and organize current sheet crossings across the magnetopause and see which ones are reconnection and which ones are not, you get the blue circles are at Earth where you see reconnection, and the red circles are not, and right across them is this condition for diamagnetic suppression. If you take now what folks have looked at across all different planets, planetary bodies in the solar system and at the heliopause, you can see that the dynamic range of types of events, both in the change in plasma beta across the magnetopause and in the shear angle that you observe, it's much larger, but the ordering is the same. And so the same criteria really hold and help to organize this data. And so this criteria seems to be pretty robust no matter what planet you're looking at. And that's really important, because if you go to the next slide, thinking about when reconnection can happen, what stops it from happening, and then the geometries in which it can happen are all important pieces of understanding how much energy you can actually get from your system. And so what you get is one model that's been really effective at Earth, and then even at other planets, the maximum magnetic shear model, where you drape take a model of the magnetosheath draping across the field, and then determine sort of along the primary X line where you expect to get reconnection occurring. And that seems to be pretty good at, and especially when you don't have strong radial IMF, which in the outer heliosphere you don't, really good at predicting where you see these signatures of reconnection. And so we can use this as a guide to tell us about where on a magnetopause reconnection can happen and what types of geometries we can expect. The next slide, please. Likewise, if you look at different magnetopause crossings, they look very similar. This is data from Rob Ebert's paper at Jupiter, at the magnetopause, where they see a jet, and Yuki Harada's paper at Mars. You see really similar current sheet crossings. You see similar reconnection signatures. And a lot of these plots even similar, you can organize in the right coordinate system. And these events look very similar, even though they're very different environments. And so you can actually use these and reliably use these throughout the solar system to understand, is reconnection happening where my spacecraft, and I have the right measurements to infer that. Go to the next slide, please. And what I said is true, but you could also get some subtleties at different planets. For example, just flux transfer events, for example, just look different depending on where you are. At Saturn, here's an example from Jimmy Jasinski, where he sees an FTE at the magnetopause, where it's this nice large-scale flux rope. And at Mercury, this is work for Wei Ji Sun, these things occur in flux transfer event showers, and so you just see so many of them and so rapid and so large amplitude. But it's still a flux transfer event in the magnetopause, and they impact the flux budgets at the different planets very differently, but it's still reconnection that's happening to give you these things in roughly the same type of regions. Next slide, please. And one thing that's really important as you try to scale how much energy you can get from reconnection to different planets is the geometry. And so you might take the slides on the left, the panels show kind of if you just took the thing we do at Earth, or that has been done at Earth blindly, and apply it to different planets, you might get into trouble. So there's a sort of a scaling, a Parallel-Akasofo parameter that talks about how you couple from the solar wind to the magnetosphere. And that's, there have been a number of different coupling functions over the decades. This in particular one tried to match the type of energy input you get from substorms with what was actually observed. And so they kind of tuned it to determine that at Earth you get this rough equivalent area of reconnection happening and energy conversion of that white circle, which corresponds to, say, what you could do now. You could scale that exact same area to Jupiter and Uranus, for example, and get estimates of how much energy you can get those different systems. But then if you alternatively think about the coupling between the solar wind and magnetosphere in terms of a dominant primary X line, kind of like how maximum magnetic shear model might predict. You can take the equivalent area of that X line and map it, and you get something similar to what Parallel-Akasofo predicted in the top panel. And then if you scale that at the different planets, you'll get a completely different result. For example, at Jupiter, you'll get a much smaller area, and at Uranus you'll get a larger area than you might predict based on just scaling things from Earth, without trying to model the fact that this is magnetic reconnection, and we kind of know roughly how that might occur. Next slide, please. And so one thing that we looked at was you can determine the efficiency of flow obstacle reconnection with respect to Earth by using scalings like that, understanding how that area might change for the different obstacles. And you can see something that kind of confirms our expectations is that Jupiter and Saturn are not particularly efficient at extracting energy from the solar wind. They have mostly internally driven dynamics. And things like Mercury in particular is really efficient at extracting energy from the solar wind. And curiously, Uranus and Neptune seem to be a little more efficient than Earth when you look at a scaling like this, which is really interesting. And we'll talk a little more about the actual energy you can get. But first, if you go to the next slide, I want to mention Kelvin-Helmholtz. And so this is another really important process for transporting energy. And you get this manifesting as you can kind of see this in observations, but it's often easier to see in the models. But from Mercury all the way to Jupiter, you are getting these type of instabilities and shear-based instabilities flowing. You get different regimes depending on what you're planted on, but you do see that these vortices, the growth is magnetopause, especially on the flanks, is ripe for this type of growth. If you go to the next slide, one thing I want to mention is some work by Adam Masters, who looked at the conditions for how you can generate or Kelvin-Helmholtz instability. And so really, once the time you get to the outer heliosphere, magnetopause are really Kelvin-Helmholtz unstable, in particular at the flanks all the time. And so you can really get this continuous Kelvin-Helmholtz instability growth. But you could also get that at the same time with sometimes, especially on the day side, drape fields, and you can have that happening at the same time as reconnection. And these are things that the coupling between those two things, rather than an either or, can be something that's really difficult to model. So sort of separating them here, but understanding it's much more complex than that. So in terms of, if you go to the next slide, actually quantifying how much energy we're talking about, one thing we did was try to parameterize external power into a magnetosphere. And by doing that, we're thinking about the energy flux through a surface. And so there's a characteristic velocity, energy density, and an area, so two length scales to deal with. When we think about magnetic reconnection, that velocity is the Alfvén speed, the outflow speed. Kelvin-Helmholtz is going to be the flow speed or differential flow speed. Energy density is going to be the magnetic energy density for reconnection, the RAM energy density or flow energy density for Kelvin-Helmholtz. And then when you think about the scale sizes that we care about for energy conversion, a reconnection, one of them is going to need to be the ion inertial length and the size of the exhaust, and the other is going to be physically the size of the obstacle or X line that you're actually reconnecting. When it comes to Kelvin-Helmholtz, of course, the obstacle size is going to be an important scalar, but ultimately it's kind of the plasma sheet thickness that you're working with, which might be a little bit different for the different planets. And so one thing we did in this paper that's come out, and I refer you to some of the details, was come out with these scaling laws for how much you can quantitative scaling logs that we kind of tuned as best we could to Earth and other planets to get at an actual estimate of, for a given set of upstream conditions, how much energy you can actually get into the magnetosphere. And you can combine that with the thing on the bottom, which is the actual solar EUV energy input. And we can compare the energy input we would expect from reconnection, from Kelvin-Helmholtz, and from just sunlight. So the next slide, please. So one thing we did was look at, in particular for the outer planets, what does the solar wind and solar EUV look like? So we were able to come up with a scaling of, based on sunspot number, the EUV flux, which you can see in the same panel, and you can see how that does go up and down with solar cycle. The average dynamic pressure, these are, I think, monthly averages of the solar wind scaled by our heliocentric distance, which you can see is relatively constant, much less strongly varying with solar activity, or less clear correlation. And then you look at the upstream Alfvén Mach number, which has a really strong, as talked about, solar cycle dependence. You see this modulation where the lowest Alfvén Mach numbers are during solar maximum, and at solar min you have them much larger. And then we looked at the IMF. In particular, this plot really is how different is the IMF from the tangential direction in the outer heliosphere. How different is it from the Parker spiral? And ultimately, it stays pretty constant. It's not really getting closer or further away from the Parker spiral direction with solar activity. You're just kind of seeing this constant 30-degree cone on average about the Parker spiral direction. And of course, you can take into account planetary season and magnetospheric configuration. And so one thing that we wanted to look at here is that we're not trying to predict the solar wind at Neptune. That's impossible to do with current tools. We don't have an upstream monitor. While some of the tools that propagate the solar wind are really helpful, instantaneously saying that this is what it is a really difficult thing to do. But if you're just looking at the average sense, we're looking at climatological averages of energy input into a system. It's okay to take the average conditions of the last few decades and try to understand how much energy we could have entered into that system. So we're not trying to predict a particular event. We're really just trying to understand really long-term averages. And so from that, we think we're justified in scaling the 1AU data from there so that we can understand on average what's going on. Go to the next slide, please. And one thing that, of course, is important is magnetospheric configuration. So we looked at, as a function of planetary season, solstice to equinox, what is the histogram of magnetic shear angles, say, at the subsolar point, at the magnetopause? And you see some interesting things. First, you see Earth, Jupiter, and Saturn. There's a little bit of seasonal dependence, but ultimately it's not too much. And the top panels of the actual histogram of the magnetic fields. The second panels are scaled by sine cubed of the shear angle to calculate the effective power. And then the third panels are extracting out how much reconnection efficiency you'll get for these different configurations for different Alfvénic Mach numbers. And so for the higher Alfvénic Mach numbers, you get much lower efficient, much less reconnection happening. And when you get a really low Alfvénic Mach number, you can sort of max out the efficiency of the average efficiency of the reconnection that you'll get is about 40%. Understanding that, while we can get really, we get anti-parallel reconnection sometimes during storms, on average, it's basically 90 degrees between the planetary field and the IMF, really, no matter where you go. In particular, you can see that some of these plots get a little weird, in particular for Uranus, but once you average everything out, ultimately, they kind of look pretty similar, where you have you don't see really strong average seasonal effects, even though instantaneously you'll get some interesting wacky behavior. So putting this all together in the next slide, we combine those efficiencies based on the planetary configuration with the upstream conditions, and we tried to calculate those values for energy conversion rates that you can get at the magnetopause. So the top panel is the average solar EUV energy. The middle panel is the energy you can get for magnetic reconnection, and the bottom is from Kelvin-Helmholtz. So when you look at these, you can see that as we saw before, the EUV and reconnection really vary strongly by solar cycle. The EUV varies about a factor of 2. So the reconnection varies by about a factor of 4. And the Kelvin-Helmholtz doesn't vary too much. You couldn't tell just by looking at the bottom plot necessarily when solar min or solar max were. And you can see where you get where the different planets kind of lie on, which I'll elaborate in a second. But you do see that, in particular, Earth has a really strong EUV, and Jupiter has a slightly stronger EUV than Earth, just because it is so massive, even though it's further out. And of course, Uranus, Neptune have really weak EUV energy inputs, and in fact, weakest energy inputs across the board. But the relative energy partitioning between those may be different across the different systems. So if you go to the next slide. So we'll start with Earth, and so the plot on the right shows the relative energy partitions. The blue is the EUV, the yellow is reconnection, the green is Kelvin-Helmholtz, and it's power as a function of sunspots. So solar min's on the left, solar max is on the right. So at Earth, you can see that the blue is the biggest piece of the pie, really at all the time. And so solar EUV is dominating the total energy input you're going to get, and ultimately providing that energy needed to make the thermosphere look the way it does. You can get some average energy input through Kelvin-Helmholtz. Largely, you're getting a lot of energy through reconnection, which we know is certainly true at Earth, is that you can get magnetic reconnection, you can get that lead to substorms and a lot of energy input at Earth. And you're getting, if you look at the amounts that you're getting, it's maybe a couple hundred gigawatts. That's ultimately the type of energy you need to power the aurora, which of course we know is powered by magnetospheric activity. If you go to the next slide, you look at Jupiter and Saturn. If you add together Kelvin-Helmholtz and reconnection, it does exceed the solar EUV. But ultimately, you're just not getting anywhere near the energies you need to power their particular auroras, which also makes sense because we know that those are from internal processes. And so you can get quite a boost from the solar wind. You can get more energy from the solar wind than you can from sunlight at these places. But ultimately, that energy is not necessarily going into generating the main aurora at those planets. But you can see Kelvin-Helmholtz is particularly strong at Jupiter and Saturn, also consistent with our expectations of these systems. And the next slide. And so finally, when we think about Uranus and Neptune, which you mentioned were the least explored, you really see that reconnection appears to really dominate all the energies, really at all, both solar minimum and maximum. And interestingly enough, when you add up the type of energy that you can get input from the solar wind, it's about right to power the aurora at those particular planets, the auroral emissions. And so it may be that you have at Uranus and Neptune, it may be that their weaker aurora can be explained by solar wind energy input being processed the magnetosphere, as opposed to something more internally driven, such as at Jupiter and Saturn. And so my last slide's next. And so just some takeaways. I think it's definitely true that the Kelvin-Helmholtz instability growth is more favorable than the other solar system. When you actually quantify how much energy you can get, it really becomes limited, especially to compare to some of the other sources. When you combine KH and reconnection at the different planets, it does look like at all the giant planets, that exceeds what you can get from the solar EUV, which is kind of neat that the solar wind really outshines, so to speak, the sun at those planets. I think that if you kind of look at this, the solar activity, especially with regard to reconnection and upstream alpha Mach number, really plays a strong role in the solar wind magnetosphere coupling, potentially much more than planetary season when you look on averages. A given day might not be true, but if you look at averages and how, assuming that the Parker spiral kind of stays on average the Parker spiral and the planet's just kind of moving around that, you really are seeing much more strong solar cycle variations than seasonal. And one thing that this type of analysis gets us is suggestion that the solar wind might be the source of that energy needed at Uranus and Neptune. And that when we study these processes, in particular, the connection between how much energy you can get in, the pathways for that to actually get to the thermosphere, and how that can get redistributed, is really important to study at Earth, like at GDC and also at the other planets. And one final thing I want to mention is that the plot in the bottom are some recent observations from Chavez et al. And what they show is that the clouds on Neptune seem to have this solar cycle dependence. And you can think, well, that's actually, if you just think about it in terms of the solar EUV variation, it might be difficult to explain that. Well, that does have some solar cycle variations. Maybe it can't provide that energy. If you take reconnection as this ultimate source of energy from Neptune's magnetosphere, understand that it has a strong solar cycle variation that's even stronger than the EUV. It might help explain some of these type of activities. And so I think it's a really interesting thing to think about the magnetospheric, ionospheric, thermospheric, and below connections at these planets. So thank you.
Excellent. Thanks for a really cool talk, Dan. Um, I did have one quick question regarding Uranus. I believe it's the one that's tilted, both its spin plane and its dipole relative to the equatorial plane, right? Of the
Hmm.
heliosphere. It's quite tilted.
Yeah.
And so it's interesting. I would have thought you would have seen more variations with reconnection because of that odd magnetic field topology there. Does it just really average out that the solar wind IMF is relatively random and relatively average enough that you still get quite efficient reconnection there, I guess?
And there's some interesting. I mean, it's a really good question. There's some interesting work that Carol Patty did a study on this, but ultimately, there'll be let's just take the extreme case where you have the Parker spiral IMF, and then it's really the planet doing some wacky things with its rotation. Well, at one phase of the rotation cycle, you can get reconnection, and it's almost anti-parallel, and then the other phase, it's almost parallel and shear lined reconnection. And so you can imagine those probably in an instantaneous sense. Yes, there's going to be a big difference. If you were looking over the course of 24 hours, that's going to make a huge difference. If you look
Mhm.
over the course of a month, if you average together the energy input that's just has like a 50% duty cycle, I think it can come out in a wash.
That's really interesting that happens, that it comes out in a wash. That's pretty neat. Um, so we don't have any other questions today. Oh no, we have one. I was wondering how much the moons of the giant planets contribute to the internal energy input.
A lot. Well, it depends where you are. So Jupiter and Saturn, it's a lot, and so that's really the source of most of the plasma in those environments. So in Jupiter, the volcanic moon of Io, Saturn and Enceladus, and so when you fly through those magnetospheres, you're mostly seeing those plasmas. And that mass loading really fundamentally it inflates the magnetosphere, it creates magnetodisks, and that's really a lot of the source of this sort of systematic, sustained main aurora that you see at those planets. And so it really dominates. The external stuff, I think, is likely to play a much stronger role at Uranus and Neptune. And I think there are some opportunities for certain auroral phenomena, for example, to be explained by kind of the substorm equivalent at Jupiter and Saturn, but it's much harder, say, nut to crack, where it's really the moons playing a big role and the internal energy input there.
Excellent, very cool. So if we don't have any other questions, no, one more coming up now. Um, how about the reconnection rate in these giant planets? Does it vary with respect to the size of the magnetopause and density of the plasma in the magnetosphere?
So the reconnection, and it's interesting to it depends on what words you use. The reconnection rate, and we find from MMS data and everywhere you look when you try to calculate it, it's still around like zero point 0.1, zero point 0.2 when you actually think of the reconnection rate. The energy conversion rate, which does scale some of these parameters, does change. And so a lot of people do studies about reconnection electric fields, but if you actually want to talk about the energy input, you do need to think about the scale sizes. And so that it's the ion inertial length in particular that's really important, which is directly related to the density at the magnetopause. And so part of the difference you see is not only the in reconnection rate for something that's the same size, but it really does depend on what that density at the magnetopause is to get you your ion inertial length, which is going to set this fundamental scale size of how much energy you can actually get across.
Cool. And I'm just going to wait to make sure no other questions pop up again. But it doesn't look like it. So thanks again, Dan. This was really cool. I don't know if you've heard of Storm, but I think some of the stuff you've done here could be quite relevant for the Storm mission that David Sybeck is working on. So I will be sure to forward this to him.
Right.
Um,
Sorry for the technical difficulties, but thank you for having me.
we're going to take a short 2 week break coming up within the next 2 Mondays. But Simon Walker will be following up on October 28th with a discussion on the ionospheric leg of the substorm current wedge, combining iridium and ground-based magnetometer data. So I hope everyone can join us on October 28th. And thank you again, Dan, and I hope everyone has a wonderful week.
Thanks.